Good morning, everybody. So today we're going to look at simulation diagrams, simplification of simulation diagrams. We did simulation diagrams in the last lecture, and the objective was to convert differential equations or any sort of functions in the Laplace domain into simulation diagrams to give us a representation, a better representation of this transfer function, or basically how the internal variables in a set of transfer functions are related. And you will see that most of the simulations that we are doing, they kind of require two independent functions, but the functions are still interconnected. And when you look at the functions themselves, we can't really see that dependency. But when you create a simulation diagram, we can see how variables flow from one part of the system to another. So what we did in the last lecture was to go from differential equations to simulation diagrams. And today we're going to do the opposite. We're going to go from a simulation diagram back to a transfer function. And you may wonder, why are we doing that? Well, that will not only help us manipulate and understand simulation diagrams better, but also most of the time when you're creating these simulation diagrams or creating a transfer function, you may start from the simulation diagram because that's more intuitive. We can see how the different pieces of a system can be put together, and you can start from the simulation diagram and then go all the way back to a transfer function between the input and the output. So that's the objective today, is to take any simulation diagram and calculate the transfer function. Now, this is a bit more complicated than the other way, and it's one of the topics that students struggle the most. Convolution is one. Simplification of simulation diagrams is another one, and Bode plots is another one that will come up later. But we'll see with some practice, there's nothing too difficult about it. We just need to practice. And there are 7 examples in this lecture with full solutions. So go through them once we are done here, attempt them on your own. And then if you need help, you can watch the video solutions that are linked in each exercise. Okay. So it might seem a bit complicated at first, but we'll see it's not that hard. So let's get to it. So today we're going to simplify block diagrams and find the transfer function of a closed loop system or the transfer function of a simulation diagram. But there are many applications to this, as I was saying. And here is one, for example. Let's assume that we came up with this block diagram, and this here represents the position control of a rocket. So on one side, if you're controlling the position, the output of the system is the position itself. So let's call this h of s for the actual position. And on the other side here, we have the desired position of the rocket. And then it goes through through the system of equations. For example, each of these blocks could be represented by a transfer function, and you can come up with these transfer functions independently and then establish the order they interact using a block diagram. Now the question is, what is the transfer function between the output and the input of the system? What is h of s divided by hd of s? And we can use the tools we're going to see today to answer that question. In the last lecture, we used this example to come up with a simulation diagram. We have a set of transfer functions. This governs the behavior of a spacecraft, if you remember, and we came up with the simulation diagram for it. Now let's do the other way around. From the simulation diagram that you get from this, what is the transfer function between the input and the output? That's something we can explore with the tools you're going to see today. Here is a more complex system. Here we have more than one input on this side, and we have 2 outputs on the other side. So now there are a bunch of different transfer functions we can come up with here, assuming that the system is linear. Superposition applies, meaning that we can evaluate the output of the system to one input only, and then add all the transfer functions for individual inputs together. That gives us the result for more than one input. So we could ask for, or we could find any of these 4 transfer functions. And the question is, again, how do we do that for a complex system such as this one? So before we go into that, let's just do a quick summary of what we saw in the last lecture. We came up with block diagrams to simulate a system, and the idea was to represent them using graphical representation. Here again is the relation that between the input and the output of a system. In this particular case, we're dealing with voltage input to a DC motor, and the output is its angular position. Or in the case that we just saw, we may have more than one input and more than one output, and they can also be represented by a single block diagram that we see here. We had three basic operations. The first one is the multiplication, is a transfer function g of s, and you remember that at the output here, y is simply g of s times x of s. Right, the second one is also multiplication, but because it's not a function of s, we're going to call that a gain, and the gain is represented by a triangle. The triangle just tells us that there is not a function of s, it is simply it's simply a multiplication. So if you call this signal y, we have y equals to x times alpha. And the last one is the sum. If you call the output of the sum z, we can write that z equals to x plus y. And of course, if you put a negative sign around here, z is x minus y. And then if you move the negative sign to x, then you have y minus x. All right, nothing new here. This is from the last lecture. So with these three basic tools, we can create simulation diagrams. Now the question is, let's go from a simulation diagram back to a transfer function. To do that, we now need to find special operations or elementary operations that we're going to apply to these block diagrams to simplify them. And the first one, and the most intuitive one, is to combine blocks in cascade. In this example here, we have two transfer functions in cascade. The input is x, the output is y. What is the equation for the output here? It's simply the multiplication of them. All right, so that is g of s times h of s times x of s, which means that we could replace those two blocks with an equivalent block g of s times h of s. And again, the output of the system here remains precisely the same. Does that make sense? All right, so things in cascade are, we can simply multiply them and put them together in the same simulation block. Yeah. Okay, this is the most fundamental operation we can do. Now let's do some other special operations that will help us simulate, simplify these blocks. The next one is moving a pickoff point ahead of a block. Let's assume that we are dealing with this signal here. And for example, there is a function there. There's a function g of s. We know that h of s and g of s are in cascade, so we could potentially multiply them. The problem is we can't multiply them right now because we need the signal in between. Now, if you multiply them, then the signal in between is lost, and then we can't continue the feedback. So what we could do instead is to take this point where we are probing the signal and move this away from there. In this case, you're going to move this ahead of a block. So now let's see what we did here. The signal that you are interested here is y. That's signal y. If we now move the pickoff point, which is, let me write here, y equals to x times h of s, isn't it? If you now take this point and move it ahead of the block, we need to multiply the signal by h of s so that y is still h of s times x of s. If you don't add that block, then you're now changing the signal. Now y becomes x, which is not the same. What we are doing is moving it ahead, and when you move it ahead, we have to multiply it by h of s. All right, so the signal is kept the same and nothing changed. And now, if there are other blocks over here, we can combine them, and we maintained the same signal that we needed in the beginning. Does that make sense? The problem with the first one is there is really no problem with the first one. We could maintain as it is, but I'm assuming, for example, that we want to simplify this block diagram with a block diagram that is in cascade. So we know that we can multiply G and H, but if you do that, then the signal Y that we need here for another part of the simulation is gone. All right, so we need to maintain that signal there somehow. And if you want to now multiply G and H, we need to take this point and move it somewhere else, but to maintain Y the same value. But we can't just move it ahead because now Y becomes X. And originally Y is X times H. So that's why we add that, right, to maintain the signal the same. And now if there is other stuff here, we can combine everybody and continue the simplification. Yeah? Okay. Well, let's do the opposite now. Well, let's do another one. Now it's moving a summing point ahead of a block. If you take that sum and move it ahead of a block, for whatever reason we want to do that, how do we maintain the signals the same? Let's start by finding the equation for Y. What is Y here? What is the equation for Y? Very good. X plus Z multiplied by H of S, which is the same as H times X plus Z times X. Now, if for whatever reason we want this sum to go to the other side of the block, we can't simply do that because we'll be changing the signal. Now we now have X times H plus Z. So what should go in that empty block? Exactly. We should multiply that by H of S. So now the signal Y is X times H of S plus Z times H of S, which is the same as H of Z X plus H of S X plus Z. Right. So this way we maintain the output of the system exactly the same. It doesn't change. It's an equivalent model. You may ask once again, why are we adding more stuff to this? The objective is to simplify. Well, maybe because there was another block diagram block here that I want to combine with H, but the sum is in the way. So I move the sum away first and then I combine them. Yeah. Does that make sense? So you see, there is a common pattern here. When you move stuff around, we want the signals to remain exactly the same. We don't want them to change. And you do the appropriate manipulation. We add stuff whenever necessary to keep the signals the same. Now let's do the opposite. We are moving the sum ahead of the point, excuse me, behind the block. So the sum is here, and you want this sum to go over there. What do we do now? Well, let's see what the output signal is. Let's call the signal P. And what is the equation of P? P is X times H of S plus Z. Yeah. Now, if you move the peak of the sum behind the block, let's call the signal P. And what is P here? P is X times, excuse me, X plus Z times something, everything multiplied by H of S. And this something is what goes in this block. And what should that be? 1 over H of S. Very good. 1 over H of S. Because now when you put 1 over H of S here, we can multiply this out and we have X times H of S plus Z, which is precisely what we started with. Okay. Any questions here? Folks from home, you can always ask questions using your mic, and we'll hear you here in the hall.
Yeah, I had a question about the first simulation block set. When we're adding Y and Z, what happens to y? Are we just ignoring it? Like, is it just equivalent to p? I'm just a little confused on how we're able to say that y is equal to p because we're summing that.
Right. Okay. Yeah. So this might be a bit misleading. But what I did here is I'll call the output of the system, the signal on the right here, I call that P. Because we moved away the peak off point, the sum, then the signal at this point is still Y, but is now P, because we moved the sum away. So those two signals now remain, become the same. Let's put it this way. If we had a sum in here, a gain, let's put it this way. Let's assume we have Y, then you had a gain K, and then you had P. If K equals to 1, then you see that a Y equals to P, right? And I did the same thing. I just moved away the sum. I could take that again. In this case, you know that P equals to K times Y. If K is 1, then Y equals to P. In what I did here is P equals to Y plus Z. Because Z went now the other way, Z is 0. So P equals to Z. Does that make sense?
Yeah, I think that makes sense. Thank you.
No problem. Any other questions? No? Should we move on? Okay. All right. So here is another operation, and this is probably the most important one, is to eliminate a feedback loop. And these feedback loops will always come up. You'll always see, if you have already started your second assignment, you see that there are two equations, and some equations feed on each other, and there are feedback loops and so on. Right? So these feedback loops are inherent to any differential equation. If you have a differential equation, you will see a feedback loop. So eliminating them is essential. So how do we do that? And you'll see this is a recipe, one of the few recipes that we can always use in this course. Right? The question is, what is the equivalent transfer function y over x? Well, to do that, let's start by creating an equation for y. If we call the signal here epsilon, what is epsilon? Epsilon is x minus y. And you know that y is h of s times that. So we can say that y equals to x minus y all times h of s. Does that make sense? Yeah? Sure? Okay. So now if you are solving for y or x, we can group y's on the left side. So multiply it out. We have y plus y times h of s equals to x times h of s. We can now factor out y, 1 plus h of s equals to x times h of s. And you can solve for y, the output of the system, as h of s divided by 1 plus h of s times x. And you can now see that the relation between the input and the output is the line function h of s divided by 1 plus the same function. And this is always the case when you have a feedback loop. Right? So if the feedback loop is negative, is h of s divided by 1 plus h of s. So which means that we can replace this with h of s divided by 1 plus h of s. And this is the equivalent block diagram without the feedback loop. Yeah. Now, you see that this is a negative feedback loop because the sum there has a negative sign. What happens if you put a positive sign here? Well, we can rewrite the equation. The equation now becomes y equals to x plus y times h of s. We have y now minus y h of s equals to x h of s. Y multiplies 1 minus h of s equals to x h of s, which means that y equals to h of s divided by 1 minus h of s times x of s. So with a negative feedback loop, we have a positive denominator, 1 plus. And with a positive feedback loop, now we have the negative 1 minus h of s. And this is always true whenever we have a feedback loop like this one. You don't need to go through all these steps every single time. We know that the result is 1 divided, the line function divided by 1 plus or minus the same function, depending on the sign in the sum. And this is always true.
Could you repeat? Sorry. Could you repeat, is the block diagram on the left, that's a negative feedback loop?
Yes, so the block diagram on the left initially had a negative sign.
Oh, okay, perfect. Yeah. Thank you.
And for some reason it's not updating now. Yeah, had a negative there. Yeah. All right, so with a negative sign, we go here, and with a positive feedback loop, we'll go there. All right, so the only difference is that you're flipping the sign now. Okay. Are we good? Now, one thing about this feedback loop is that this is what you call a unit feedback loop, because y is fed back into the input and is not multiplied by anything. Right? The error there, the epsilon there, is x minus y. Y is just fed back; it's not multiplied by anything, and in that case, we call it a unit feedback loop. What if we had a function in the way? Well, let's see how that goes. We can give me the expression for y. What is y? Exactly. Very good. X minus y times g of s, all multiplied by h of s. All right, so here we have g times y. Here we have x minus g times y. And you multiply that result that by h, we get y. We can now do the same we did before, solve for y by moving to this side all y's and keeping all x's on the other side. We can now factor out here y g of s h of s equals to that. And so for y as h of s divided by 1 plus g of s times h of s, everything times x. And this is now the equivalent transfer function. Now notice that the only difference is that a g of s shows up in the denominator. In our previous example, g of s was 1, and you had h of s divided by 1 plus h of s. Now g of s is not 1, so it's in the way, and you have that showing up in the multiplication. So we can simplify this block diagram as h of s divided by 1 plus h of s g of s. And you guessed, if we have a positive sign, what would be the transfer function? If this is now a positive feedback loop, transfer function would be the line function divided by 1 minus the multiplication of them. Using the same procedure we just did, we just flip the sign in the sum. So this sign here flips, and when you move y to the right side, the left side of the equation, then it becomes negative. All right, so for positive feedback loop, here's a negative sign. For negative feedback loops, we have the positive sign. And it is pretty much the same idea. Okay, so two simple rules here to remember. Whenever we have this sort of structure, the transfer function is the line function, that is the top function that goes forward, that is h in this case, divided by 1 plus or minus the multiplication of the line function and the feedback function. If the feedback function is not there, that means g is 1. Then you simply have h divided by 1 plus h or 1 minus h, depending on the sign of the feedback loop. Yeah? Any questions? All good? Okay, so what is the closed loop transfer function here? This is a very generic structure. We have a process, whatever you're trying to control, an actuator that provides inputs to a controller and a sensor. What is the transfer function y over x? What can we do? Well, first, we can combine all these three transfer functions because they are in cascade, and they can be put into one, and that is C of S times A of S times G of S. What else can we do? Well, we have now a feedback loop with that function, and the feedback loop has a function H of S. And notice here, the sum has a negative sign. This is a negative feedback loop. We can now find an expression for y as the line function, the top function. So that's C A G of S divided by 1 plus, because that's negative, the multiplication of the line function and the feedback function, C of S, A of S, G of S, and don't forget H of S. Yeah, in this case here, H on top would be CAG, and our G is H. So it's flipped, but you get the idea. Yeah? Questions? No?
Where is x in this equation? Do we not multiply it by the cascade of functions at the top, or?
Oh, definitely, yes. I forgot it. X.
Okay, thank you.
Okay, so now you see we can put this function in the block diagram and have the same structure we had before. Yeah, can forget X, that's the input to the system. We did a DC motor in the last lecture. Now let's try to find its transfer function. The question is, what is the transfer function between the input voltage and the speed that for some reason here is called V of S? What do we do? Well, to do that, we need to set t to 0. That's what the problem says. We can only find transfer function between one input and one output at a time. So if you want V, actually, I read it wrong. The transfer function that you're looking for is the position divided by the input's voltage. Okay, for t equals to 0. How do we do that? First step would be, if t is 0, what can we do first? We can multiply these three elements together. When t is 0, that sum doesn't do anything. That sum can go away, and you are left with the multiplication of those three blocks. And the multiplication here is simply ki over ls plus r times js plus b. What would be the second step? What would be the second step? Right, so now we can get rid of the feedback loop, very good. And once you get rid of the feedback loop, what do? Multiply that by the next cascade function, which is 1 over s. Et voila, we have our transfer function. So now let's do that. So how to eliminate the feedback loop? Let's create this transfer function here. We are now want to eliminate that feedback loop, and that is the line function, which is ki divided by ls plus r times js plus b divided by 1 plus the same function but also multiplied by the feedback function km. All right, so that's we'll deal with the inputs and outputs later. Let's just eliminate that feedback loop first. So that entire thing simplifies to this. And what can we do next? Well, we can find a common denominator in the denominator of this equation. And you have ki over lsr js plus b. The common denominator here is lsr js plus b, and we have that times 1, so ls plus r js plus b plus ki km. Now we see that the denominator and the denominator here will cancel out, and this simplifies to ki over the result here, km. Okay. Now let's not lose track of what we are doing. Let's go back to the simulation diagram and rewrite that with the simplifications we established so far. So we have v of s going in. We eliminated the feedback loop, and the entire feedback loop now becomes the function we just calculated. All right. And in the output here, we have ws 1 over s theta s. So what is the equation for theta of s now? It's simply the multiplication of these two line functions. Is this times 1 over s, and of course times v of s. So we can now find the transfer function theta over v. Right? They're just dividing both sides of the equation by v of s. Let me just move this here because I think the folks at home there have my image on top of it. So under here, if you can see it, is 1 over s. All right, now the transfer function is simply obtained by now dividing both sides of the equation by v of s. Yeah? Any questions? No? Okay, so if there are no questions, let's do something a bit more complicated. I'm going to skip this slide here. This is just for information. Let's do this guy here. Find the transfer function y over r in here. All right, so let's look at this. And let me ask you the following question. What is the first step? And really the most important thing about this simplifications is to find the right first step to start the simplification. And now, of course, you have to think ahead and see what happens after that step you are proposing. How are we going to continue once we take this first step? So what can we do here? Right, straight away, we can look at it. There's nothing we can do. We cannot multiply anything. We cannot eliminate any feedback loop. There is literally nothing that can be done right away in this, because there's always something in the way. This feedback loop cannot be eliminated, because if you eliminate the feedback loop, this signal disappears. And then what are you going to find it? We can't multiply these two signals for the same reason. There's a signal between them. We can't multiply these in cascade because we need signals that are in between. So clearly, we'll have to move some stuff around first before we start that simplification. Any ideas for how to start? Aha, excellent, excellent, very good. So the suggestion is we could multiply these two, but there is a signal in the way. So let's take that signal away. And where could that signal go? Well, we could put the signal ahead here, or we could put the signal behind G4, after G4. Which one is better? Oh, they are both correct. Which one helps us with further simplifications? Moving it, well, if you move it back ahead of G3, then we'll have a problem later with this feedback loop. Right? Because the signal is still there, still bothering us. If we take this signal and move this past G4, then we can also eliminate the feedback loop and you don't have to worry about it. Right? So the first step here, which will allow us further simplifications, is to take this point and move it ahead of G4. And the reason is that you can combine G3 and G4 and you can eliminate the feedback loop there. So that's what we are going to do. We are taking this, multiplying and passing that over G4. Now, we can't simply do that because you're changing the signal. Let's put it this way. If the signal here is A, what is the signal past H4? Is A times, excuse me, H2. A times H2. If the signal we are probing is A, then in the other end of H2, we have A times H2. If we now move our signal, our pickoff point here, what we are sending to H2 now becomes A times G4. And this is what is going up now. So in the other end here, we are going to have A times H2 times G4. And we change the signal. All right, so that doesn't work. So something is missing. What is missing in the block that is left empty there? What should go in there? Exactly. We need to divide H2 by G4. And if you do that, and now we see that the signal going up is A times G4 is multiplied by H2 times G4. So G4 cancels out. And the output of that block is now A times H2 as we had originally before we started. All right, so we moved a pickoff point ahead of a block. And to maintain the same signal, we had to divide that signal by the block we jumped over. Does that make sense? Yeah? Any questions? No? Okay. So we went, that's what it did. We had here H2 over G4. And what do we do next? Well, now it's easy. Now these three guys here can be combined. Now we can eliminate that feedback loop. we can clearly multiply G3 and G4. And you remember then now we have here a positive feedback loop. And if you had a positive feedback loop with two functions, let's put it this way, A and B like that, what is the result is A divided by 1 minus AB. That's a positive feedback loop. A is G3 times G4 and B is H1. So the result there is G3, G4 divided by 1 minus G3, G4, H1. All right, so this entire block here becomes that. Yeah? That makes sense? All right. So if that makes sense, what do we do next? What is the next step? Very good. We can combine G2 with that. We simply multiply them together. And then when you do, what do we do after? Right, exactly. So now once we do that, we can simplify this feedback loop. It is a feedback loop, it just happens to be going from the top, and doesn't mathematically, that doesn't change anything. So we can combine G2 with the function we just found, and then eliminate that feedback loop. So let's do that. We'll multiply these, and we eliminate the feedback loop there. We now have a negative feedback loop. So the result is A divided by 1 plus AB, where A is the line function, the big function, and B is the function GH2 over G4. So this entire thing simplifies to this function, G2, G3, G4, divided by 1 minus G3, G4, H1, divided by 1 plus, C is a positive, a negative feedback loop, the same function, excuse me, something went wrong here, the same function, but multiplied by the feedback function H2 over G4. Yep. This 1 plus here is coming from this feedback loop that is negative, and this minus came from this feedback loop that is this feedback loop that's positive feedback loop. That's where the y comes. I think you just missed, you got a bit late. I think you missed that first part, right? Yeah. So that's where it comes from. So in this case here, what we are simplifying is has a positive feedback loop, we see a negative sign. And if there is a negative sign there, then this becomes positive. Okay. All right, so now we have to simplify this thing. And how we do that? Well, we can see that a G4 here and G4 there cancel out. We now need to find a common denominator. And let's do that. G2, G3, G4 divided by 1 minus G3, G4, H1 divided by the common denominator here is 1 minus G3, G4, H1. That multiplies 1, that is 1 minus G3, G4, H1 plus G2, G3, H2. And now the denominators on top at the bottom cancel out. And we are left with G2, G3, G4 divided by 1 minus G3, G4, H1 plus G2, G3, H2. This is getting big. Does that make sense? Yeah, it's very easy to make a mistake here. I was doing this last night and I did mess up with the signs, so be careful. What do we do next? Right, now it's easy, now it's obvious. We combine G1 with the function we just came up with, and then we eliminate the feedback loop, and that's the last step before we find our transfer functions. So here is the combined G1 and the function we just had. And now we need to find the final transfer function. And the transfer function, let's call this A, let's call this B, is going to be A divided by 1 plus AB, Y plus, because here we have a negative feedback loop. All right, so let's do that. A is G1, G2, G2, G3, G4 divided by 1 minus G3, G4, H1 plus G2, G3, H2. And this is divided by 1 plus, come on, I want to write this again there. That times H3. Right, so this is the equation for Y of S. And this is times R of S. Now we have to simplify this mass here. And how we do that, we have to find a common denominator. So let me write Y over R equals to the top function here doesn't change, but the denominator now has a common denominator, and is 1 minus G3, G4, H1 plus G2, G3, H2. So it's the same when you multiply that by 1. And then plus G1, G2, G3, G4, H3. I ran out of space there, but you get the idea. And don't forget the H3. And now the function finally simplifies because this denominator and that denominator will cancel out. And you have Y of S divided by R of S as G1, G2, G3, G4 divided by 1 minus G3, G4, H1 plus G2, G3, H2 plus G1, G2, G3, G4, H3. Whew. Nice, isn't it? All comes down to a single function. Any questions? Yep. Okay, so, back here. Between G3 and G4. Oh, this one. Yeah. 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 What is your question here? Right. So if we move the signal, if we move the signal ahead, So the signal would go here. Now the signal we were, if the signal here is now called A, the signal here is A times G3. All right, and A times G3 is what is going to H of H2. All right, but now we are just sending A. So if you do that, if you take it ahead of the point, then this should have been multiplied by H2 times G3. All right, so that is a valid operation. The problem is that now we are again stuck. All right, we are stuck again because there is that signal going up and you can't eliminate the feedback loop, but it is a valid operation. So you see, this is actually a very important question in the sense that, well, I could move ahead or behind, and then I see a lot of students just finding a first operation, which is correct, and then they get stuck. Then they undo the operation, they go back, and then they create a mess. Right? So it is very important to, when you get to a block diagram like this, to take the time and think ahead. What I do after this operation and what I do after that one. Right? So like a little puzzle. How do we best simplify the puzzle to solve it? Okay. Any other questions? No. Okay, so if there are no other questions, let's do exercise 2. Here we have an active suspension system that it can be controlled by a sensor that looks ahead at the road conditions. An example that it can accommodate road bumps is shown in the figure. Find the gain K1 so that the vehicle does not bounce, that is, the desired deflection, desired position is 0. T of S is a disturbance. So what do we have here is a suspension system like the one I have in the assignment, but this is an active suspension system. So it looks ahead what is happening in the road, and then we'll adjust the car parameters to make sure that there is no position change. So you're always on a flat surface. What do we do here? So we don't want the car to bounce, meaning that our desired position of the car is always 0. We don't want anything to move. So R of S is 0. What is T of S? T of S is something external to the system. It's something that is applied to it which could be the disturbance coming from the road, for example. So this is the road effect. And what we want is the output of the system, the position of the chassis or whatever we are controlling to not change. That stays at 0 regardless of what is coming in T of S. We can't set Y to 0. Because then there would be no point in modeling the system. We don't have control of the output of the system. We can't just fix the speed of the car at a given value. We need to adjust the throttle to control the speed, and it's the same here. We can't just fix the suspension at 0. We need a control system that will regulate the position at 0. That's what we are doing. That's why you cannot set Y to 0, but we can make our goal 0, same as the speed. We can't have the car always running at 30 kilometers an hour, but we can regulate the throttle to run around that speed. The question is, what is the value of K1 so that the output of the system is always 0, the car never bounces, despite disturbances being applied to it? So what do we do here? Well, we need an expression for Y. Let's try to find that expression. So this is a bit different than what we just did, because you're going to come up with an equation here for this. What's the signal here? Is R of S minus Y of S. What is the signal there? It's R of S minus Y of S minus K1 T of S, isn't it? What is the signal past K2? Well, it's the same, R of S minus y of s minus k1 times t of s multiplied by k2. What is the signal right there? Well, it's the same signal we had, but this signal is now multiplied by, we are subtracting t of s from it. You know what is the signal past the block? Is everything multiplied by g of s, and this is y of s, isn't it? This the signal just after g of s is y of s. Are we good with this? Any questions here? Are we good with this derivation? Yeah? Does that make sense? Okay. All right. So now what can we do here? Well, we can expand this equation. That's the equation for the system. We kind of solved for y of s, but there's still y of s in here. So let's expand this equation and see what we get. We get y of s equals to r times g, r times k2, r times k2 times g of s minus y of s times k2 times g of s minus k1 k2 t of s times g of s and minus t of s g of s. Now, we want the system to go to 0, meaning that our desired input, the input to the system is supposed to go to is 0. So this entire term here that has r of s goes to 0. And we are left with all other terms. So let's move y of s to this side here. G of s equals to t of s times g of s, and this gives minus k1 k2 minus 1. All right. So what I did here in the first part was to say, if we want the output to go to 0, then the desired input r is set to 0. If you wanted this to go to 30 kilometers an hour or to move by a certain amount, then the input would go to that amount. We can't fix the output of the system. That's why we're trying to regulate. The next thing is, the question is, what is the value of k1 so that the system always goes to 0 regardless of the value of ts? So this is saying, what is k1 so that the result of this is always 0? Y is 0. So if y is 0, we have 0 equals to t of s g of s minus k1 k2 minus 1, which means that a negative k1 k2 equals to negative 1, k1 equals to negative 1 over k2. So if this condition is met, then whatever we put in t of s will result in a 0 displacement in the output. In other words, whatever happens to the road doesn't matter, because y is always 0 regardless of t. Okay, so there is a bit of there's a weird concept here of regulation of the output, but don't worry about that. I think the message is really to just come up with the transfer function. So look at the diagram and come up with the transfer function. I'll be in the specifics of the problem about this road example are not important. Okay, so the idea again is to just be able to come up with a transfer function by looking at the diagram. And you'll notice that here we did things a bit differently. We just created an expression by labeling the signal. In the example we did before, that would have been much more complicated. So it's that way is better to go with a simplification right away. Any questions? No? No questions? Okay, so if there are no questions, let's do another one. I have this one. We did the last lecture. We came up with this block diagram, and now we can go backwards. But this, I think, is trivial now. So I'm going to skip this, leave this as homework. Let's do this one instead. Aha, that's better. That's better. All right. We want the transfer function r, y over r. What do we do first? What would be the first step you would take here? Simplify the feedback loop. Which one? Sorry, I can't hear you. Can you speak up? G3 and H1, right? That we can certainly simplify. But what do we do with that triple sum? Well, that triple sum is the same as two sums in cascade, isn't it? We could replace that as sum. Let me open this up here. We could replace this sum with two sums like that. No, that's the same. That's the same thing. And if that is the same thing, now we can eliminate G3 and H1 by combining them. There is another operation we could do right away. Look at H2 and K4. What is happening there? Is that a feedback loop? I don't think so. It's not, doesn't look like a feedback loop. But let's assume, let's call the signal here A. And let's see what these two signals inject there. When they come to that point, we have A times H2 added to A times K4 with a negative sign in front of them. All right, A times H2 times A times K4. So we could factor out A, which is the signal we want. So negative A, H2 plus K4, and put H2 and K4 in the same block. Right, because they are feeding the exact same point in the code in the block diagram. They are feeding the same point, and they are picking off the same signal A. So we can just add them up. Can you see that? Yeah. So you can do these two operations to get. Do you have a question? Oh, sorry. So you can do these two operations to begin with. Combine H2 and K4, and then simplify G3 and H1. So let's do that. Let's just start with combining H3. Let's write this from the beginning. R of S is the input. Then it feeds that. We have G1. We have G2. So that's K5. K5 feeds here. And we have K6 that feeds a sum. Then we have that. And then we have a block here that you're going to come up with. And this block is the simplification of G3 and H1. We have H of S, Y of S there. So the first thing you can do now is to simplify what is missing. Yeah, and this goes up and down. This will simplify G3 and H1. So what is the resulting function there between G3 and H1? It's a positive feedback loop. So G3 and H1 simplify to G3 divided by 1 minus G3 H1, right? Minus because it's a positive feedback loop. So this becomes G3 divided by 1 minus G3 H1. And now we have this feedback loop at the bottom there that it has K4 and H2 in them. And as we discussed, they can be put together into one sum. And then they go to that sum over there. They are both negative. You notice here, both negative. So we need a negative sign in there to compensate for that. Yeah. Does that make sense? What do we do next? What do we do next? Well, if you want to combine G2 and G1 and G2, that signal going up there needs to go away. So what it could do is to move it to the left or to the right. Where should that go? To the left or to the right? I would probably move it to the right, right? Because then you can combine G1 and G2, and then later we are free after one more step to do the feedback loop. So if I move that pickoff point between G1 and G2 to the right, so past the G2, what happens to the signal that it goes up to K5? It needs to be divided by G2. Exactly. So let's write this here. We have R of S. Here is a sum. We have now, let's call this G1, G2 is already the combination of them because we took off we removed this feedback point here, this peak off point. This peak off point goes to K5, but now it needs to be divided by G2 because you see what was going up before didn't have G2 in it. Now that we move the point to the left, we are picking off the point after the signal is multiplied by G2. And that's why I have to divide it by G2 to maintain the correct signal. Sorry, okay, I did the just mixed up here. And we have now fitting this sum. And we have that. And K2 plus H4. Okay, so what was the last operation we did again? We had this peak off point here. We moved this ahead of G2. By doing so, G1 and G2 can be combined. But I also have to divide K5 by G2 because now the signal we are sending up comes after G2. And it wasn't the case before. So we divide it to maintain the same signal. Is this clear? Does that make sense? Yeah? Okay. Yep. Yes. Yep. Okay, so what do we do next? So this next step is a bit tricky to see. We are kind of in an awkward situation here because we can't eliminate anything else. There's this sum coming from the top that is kind of messing everything up. So this one is a bit tricky. Let's look at the signal here. The signal at this point has three sources. What are they? Well, it's the signal coming from here. It's the signal coming from there. And it's the signal coming from that point. All added up. All added up. Right? So from the signal that the first one the second one I highlighted here, we have a signal going from this point through the sum and then it's being injected here. So we see that we take the output of G1, G2, multiply that by K5 over G2, then multiply it by K6, and then add that to the loop. So couldn't we just take that a K6 and move it ahead of the, or behind the sum point? Wouldn't that be the same? You wouldn't, right? You would, excuse me, you would. What it could do here, let me copy this to another slide. What I'm proposing is to take this K6 and not move it, but add this K6 to this block. So we would have something like this, R of S. Now I'm warning you, this is a bit tricky to see, but let me do it anyways. We have here, let's see if you get it, K5, K6 divided by G2. And now I'm creating a sum for that guy, like this. And then the other sum remains for this K6 that was coming after the transfer function. Now look at this, see, let me know if this makes any sense. It is a bit tricky. But do you see that this is exactly the same? This is exactly the same. Right, the signal that I was going through K2 and K5 over G2 is eventually multiplied by K6 and then injected back into the main loop. What I did is just moved K6 over there and gave it its own sum. All right, so basically what I did here was to split this sum right there, oops, this sum here into two different sums. Right? And then the system remains precisely the same. Look at what you are injecting from each loop. From the top loop, we're injecting y times K6. Well, that didn't change in my new formulation there. From the loop that we just moved, we were injecting K5 over K2 times K6, and it's precisely the same we still got. All right, so the signal remains unchanged. Any questions here? Did this manipulation make sense to you? Yeah? Sort of? Okay. Now our job is easy. So that is really the tricky manipulation in this diagram. What do we do next? right, yes, we can eliminate the feedback loop from K6 and G3 1 over that. What else can we do? We can deal with this guy here. Right, that is what is happening there. They are feeding the same point. They're picking off the same signal. How do we simplify that? Isn't that a K5, K6 over G6, G2 plus 1? Plus 1. Right? If we call the signal here A, what is the result here? Well, it's A plus A times K5, K6 over G2. Factor out A, it's K6, K5, K6 over G2 plus 1. Next step, do this transfer function, this simplification over here. Combine the line, eliminate the last feedback loop, and that's the result. Okay, I'll post that. We are running out of time, but I'll post the full solution later, and there's also a video here in the link that you can watch. There's a link in the question here. The full solution is there, but also posted here. But you get the idea now. Now the steps that we have to take, the subsequent steps are obvious. Let's combine these loops in the main line and take the feedback function to find the complete transfer function.